Hi, this is Srikanth, Assistant Professor of Triple Department. In this session, I am going to discuss about maximum power transfer theorem. In this maximum power transfer theorem, we are going to find the power absorbed by the load resistance, and when this maximum power is transferred to the load is going to be calculated. Now, this theorem is used to find the value of RL, for which there would be maximum amount of power transfer from source to load. For the transfer of maximum power, according to the maximum power transfer theorem, RL should be equals to RTH. If we take a Thevenin equivalent circuit along with the load resistance, when the load resistance is equals to the Thevenin resistance or source resistance, then the maximum power will be transferred to the load. So this is the condition where the maximum power is going to transfer, that is RL is equals to RTH. And here, even though whatever the value RTH is equals to RL, when RTH is equals to RL, we are going to get the maximum power. Less than this value, if we take the different values of load resistance, if we take the value, load resistance value is less than RTH, the power absorbed will be less. And if we go with load resistance is greater than RTH also, the power absorbed is less than the maximum value. This is the characteristics versus power versus load resistance. When the load resistance increases up to the RTH value, the maximum power increases. After that, the power will decrease. So at the condition RTH is equals to RL, the power will be maximum. And this is the statement of maximum power transfer theorem. A resistance load being connected to a DC network which receive a maximum power when load resistance is equals to internal resistance or Thevenin's equivalent of source net. So RL is equals to RS or RTH. Then the maximum power will be transferred. If we take a DC source network and load resistance, where DC source network, whatever the network which is having a DC supply, can be replaced by using the Thevenin's theorem, can be replaced with a VTH with RTH. When RL is equals to RTH, the maximum power will be transferred. Here, a variable resistance RL is connected to the DC source network as shown in the figures, which represents the Thevenin's voltage or open circuit voltage and RTH of the source network. Now, let us derive the condition, because whatever the statement we are giving, that we should have a mathematical proof. So for that, we are going to calculate the power and we are going to derive the condition for maximum power transfers. Here we are going to calculate the value of load resistance such that which receives the maximum power from DC source. So for that, I am writing I is equals to VTH by RTH plus RL. Here in this circuit, I is equals to The voltage is VTH and here it is RTH and it is the load resistance. RTH and load resistance are connected in series and which is connected parallel to the VTH. So I is equals to VTH by RTH plus RL. I is equals to VTH by RTH plus RL, where PL is equals to I square into RL, that is equals to VTH by RTH plus RL whole square into RL. Here, this is the power equation, and this will be maximum. This will be maximum, and by varying the load resistance. Hence, the maximum power can be delivered when differentiation of this equation, differentiation of power equation with respect to RL, that should be equals to 0. If that condition satisfies, then the maximum power will be transverse. So here we are taking dPL by dRL which is equals to 0, and we are having the power equation PL is equals to VTH by RTH plus RL whole square into RL, I square into RL. Here now we are going to differentiate the above equation with respect to RL. dPL by dRL, that is RTH plus, this is UV formula, so V into U dash, V into U dash. V value is RTH plus RL whole square into U dash. U dash is D into VTH square into RL by dRL minus VTH square into V U dash. Sorry, U V dash. VTH square into RL into D by dRL of RTH plus RL whole square divided by V square, that is RTH plus RL whole power 4. Now dPL by dRL is equals to VTH square into RTH plus RL whole square, that is here dRL by dRL, that will become 1 minus VTH square into RL into differentiation of RTH plus RL whole square with respect to RL is 2 times the RTH plus RL divided by RTH plus RL whole power 4. Now if we take in this equation VTH square RTH plus RL is a common term. So when we take RTH plus RL as a common term, that is VTH square into RTH plus RL, if we take common RTH plus RL minus, here we are having 2 into RL, we are having 2 into RL minus 2 RL divided by RTH plus RL whole power 4. Now if we take this RTH plus RL and this power 4 will become power cube. This is the equation we are going to get VTH square into RTH minus RL by RTH plus RL whole cube. But what is our condition? This should be equals to 0 in order to get the maximum power. So dPL by dRL which is equals to 0. When we make this equation to 0, we will get the condition, that is RTH is equals to RL. This is the way we are going to calculate the condition for maximum power. Now let us calculate what is the amount of maximum power which can be transferred from source to load. Hence, it has been proved that power transfer from DC source network to resistive network when the internal resistance of DC is equals to the load resistance, that is equals to I is equals to VTH by RTH plus RL, where power is equals to VTH by RTH plus RL whole square into RL, where RL value is same, RS is equals to RL is equals to RTH, which is equals to R, which is equals to R, where P is equals to, if we substitute this value in place of RTH and RL, if we substitute only R into 2R 2R whole square, that is 4R square into R, that R will get cancelled. We are going to get the maximum power P max is equals to Vs square by 4R. This is the condition for, this is the value of maximum power. P max is equals to Vs square by 4R. Now let us go with the example. Here, let us take the different value of load resistance, and with that how we are getting the power, and let us see what is the efficiency and how we are going to get the characteristics between the power versus load resistance. Here the source voltage, I am considering it as 10 volts and RS value is 5 ohms. Now the load resistance values, I am considering that 1 ohm, 3 ohm, 5 ohms, 7 ohms and 9 ohms. For all these conditions, we need to calculate what is the power. So here RL is equals to 1 ohm. When we substitute RL is equals to 1 ohm, that is 10 by RS plus RS, RS plus RL, that is 10 by 5 plus 1, that is 6. 10 by 6, that gives the value as 1.667 amperes, where power is equals to I square R. I square is 1.667 square into RL value is 1. So power value is 2.778 ohms. Sorry, 2.778 watts. This is the power calculation at one condition. And in the similar way, we are going to take the calculation of power at RL is equals to 3. First we will calculate the I, that is Vs by Rs plus RL, and power is equals to I square into RL. Like this, if we calculate, we are going to get the power value as 4.68 watts. And at RL is equals to 5, I, we are going to get it as 1 ampere, where power is equals to 5 watts. And this is a incremental up to this value, that is RL value is equals to 5, the power value is incremented. Then after, if we take the RL value as 7, I value will become 0.833 amperes, where power will be equals to 4.86 watts. In the same way, RL is equals to 9, I is equals to 0.714 amperes, and power is equals to 4.59 watts. So this is the way again we are going to get the decremental in the power values. So here the characteristics between power versus load resistance is up to RL is equals to RS or RTH, the power value is increasing, and then after the power value decreases only at the condition where RL is equals to RS, we are going to get the maximum power. And now let us calculate the efficiency. So power is equals to 10 into 1, that is equals to 10 watts. Power P is equals to 10 by 5 plus 5 whole square into 5, that is equals to 5 watts. So here the total power which input power is, we are going to get it as I square into RL by IS square into RS plus RL, that is equals to, which we are going to get it as 50% efficiency. This is the condition where we are going to get the 50% efficiency, because the remaining 50% is wasted in the source resistance. Here is the efficiency, that is where Rs is equals to Rs. If you substitute, we are going to get 2 into RL. So we are going to get 1 by 2 into 100%, that is equals to 50%. We are going to get the efficiency. Now let us go with another example. Now we need to calculate the value of RL for the given network below, that the power is maximum, and also find the maximum power through load resistance using maximum power transfer theorem. So here the circuit which is given with a single voltage source with some number of resistors which are connected in series or parallel, and we need to calculate what is the value of load resistance. So for that we need to convert our circuit into a Thevenin equivalent between these two terminals, as A and B, let us consider. So first let us calculate the RTH. Then after we'll go with the open circuit voltage. So for calculating the RTH, we need to make the source voltages to 0, where the source voltage, if it is a voltage source, it is replaced with a short circuit. If it is a current source, it is replaced with a open circuit. Now it is a voltage source, so it is short circuited, and when it is short circuited, this is the 6 ohm resistance, another 6 ohm resistance, 5 ohms and 2 ohms. Here the load resistance is open circuited. Now we need to calculate the RTH between these two terminals. Okay, so now we are going to check between these two terminals. So here we have to start from the extreme end of the circuit. So here the extreme end of the circuit is 6 ohms and 6 ohms. These two only we can say whether they are in series or parallel. So here the 6 ohms and 6 ohms are having different currents, and which are connected between the same nodes. So we are going to get these two resistors are connected in parallel. 6 ohms and 6 ohms are in parallel. When the resistors are connected in parallel and equal resistances are connected in parallel, R equivalent 1 is equals to whatever the resistance divided by 2, that is equals to 3 ohms. So now we got the R equivalent 1 as 3 ohms. Now we are replacing this R equivalent 1 with this two resistors, two parallel connected resistance. This is the 3 ohm resistance and 5 ohms and 2 ohms. So if you see this, you can say this 3 ohms and 2 ohms are connected in series. When 3 ohms and 2 ohms are connected in series, R equivalent 2 is equals to R1 plus R2, that is equals to 3 plus 2, 5 ohms. So this is the R equivalent to 5 ohms. Now if we replace the R equivalent 5 ohms with 5 ohms, so RTH is equals to 5 by 2, that is 2.5 amperes, because these 5 ohms and 5 ohms are connected in parallel. So now we got the RTH value is 2.5 ohms. Now we need to calculate what is the VTH. So for calculating VTH, we are going to keep the voltage as it is, and we are going to remove the load resistance. So here the load resistance is removed, that is open circuited, and source voltage is kept as it is. Now we need to write the KVLs in the both the loops. When we write the KVL, we'll get the current flowing through these 5 ohms, and voltage across this 5 ohms is nothing but current flowing through it into that particular resistance value. So if we write the KVL, this is, let us consider this as I1, this as I2. KVL in loop 1. In this, I1 is entering the negative terminal of voltage source. So minus 6 plus 6 into I1, only one current is flowing, plus 6 into I1 minus I2, 6 into I1 minus I2, because we are considering that whatever the loop current we are considering, that has higher magnitude, that is equals to 0. That is 6 plus 6, 12 I1 minus 6 I2 is equals to 0. This is KVL in loop 1. Now let us write the KVL in loop 2. KVL in loop 2, that is equals to, if we write the KVL in loop 2, that is 6 into I2 minus I1, because here the I2 current has higher magnitude, plus 5 I2 plus 2 I2 is equals to 0. So that is minus 6 I1 plus 6 plus 5, 11 plus 2, 13 I2. 13 I2 is equals to 0. Sorry, this is equals to 6. So we got the two equations and two unknowns are there. We are going to calculate by solving these equations 1 and 2. From equations 1 and 2, from equations 1 and 2, we are going to get I1 value as 0.65 amperes and I2 value as 0.3 amperes. Now we got the I1 and I2. Now I2 is nothing but current flowing through the 5 ohm resistance. So I2 value we got it as 0.3. So VTH is equals to 5 into I2. VTH is equals to 5 into I2, that is equals to 5 into 0.3, that is equals to 15 volts. Now we got the VTH as 15 volts and RTH as 5 ohms. Now let us replace the circuit with these two values. Here this is the load resistance IL, and this is the RTH. We got it as 5 ohms, and this is the VTH. We got it as 15 volts. So we got VTH and RTH, and with this we can say that when load resistance is equals to RTH, then maximum power will be transferred. This is the condition. When load resistance is equals to 5 ohms, there will be a maximum power transfers from source to load. And what is the value of maximum power? That is equals to, we got it, we are having the equation, that is Vs square by 4 into RL, that is equals to Vs value is 15 square into 4 into RL value is 5 ohms, that is equals to 11.25 watts. This is the maximum power we are going to get, that is equals to 11.25 watts. Like this we can calculate the load resistance value, where the condition which is given as maximum power is transferred from load source to load, and also the maximum value of power. In this session we have discussed what is maximum power transfer theorem and how we are going to derive the condition for maximum power transfer theorem, and some examples corresponding to the maximum power transfer theorem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.